Mathematical modeling of field problems in engineering is also one of the important topics in finite element methodology. Why we utilize mathematical modeling? Yes, which provide information for design purposes to understand the system from the model. If I develop the model with the software means from that model I can get the real life solution with the aid of mathematical modeling. So, mathematical modeling playing vital in engineering concepts. So, the modeling can be done through the two procedure which are physical resources with our laboratory, and we can perform the field experiments with the machine shop or otherwise with thermal engineering labs and fluid mechanics lab. Likewise, we can perform the field experiments. These are all the real world experiments, but which are expensive and time consuming process, so that we can utilize mathematical resources to overcome these kind of problems. Okay, so learning of mathematical modeling with the digital computers and computational methodologies are important in engineering problems. So, what is mathematical modeling? Again, I can tell you, mathematical models can be represented the real world problem in an abstract form. Okay, I won't utilize the words in mathematical forms. So I can utilize the notations in the mathematical form. So I can reduce the time consuming to write the formulations and the analysis. Okay. The different components in mathematical modeling are state variables, external variables, mathematical equations, coefficients, universal constants. Here, what is mean by state variables, which describes about the state of the system used to be modeled. If I want to model the thermal system, or if I want to model the fluid mechanics, or if I want to model the machine structure, means the state variables are available with every system. Okay, here if I consider the fluid mechanics laboratory, means the fluid has its own density, own viscosity for flowing one place to another place, so that I should consider the density and the viscosity of fluid in the mathematical formulation for defining the state variables. And then not only individual variables, external variables also plays. What are all the external variables are to be considered in mathematical modeling? Yes, forcing functions, external variables influencing on the system. Those are the external variables that are available with the mathematical modeling. And then we can get the mathematical equations from state variables and external variables. What for mathematical equations? From this, what can we infer? Yes, the mathematical equations generally develop the relationship between state variable and external variable. Not only with these three things, other things are also available. That those things are coefficients and universal constants. What is coefficient and universal constants? Let's see. Mathematical model contains these terms. Moreover, it requires calibration for finding best parameters and universal constants by variation of number of parameters. For example, if you are consider the tool life equation, Taylor tool life equation, V into 2e power n is equal to c. There V is equal to cutting velocity, T is the tool life. Every material, the tool life is varies. Every workpiece material, the tool life may be varies. So that we may introduce the exponent for that tool life parameter in that particular equation, so that we can vary the number of parameters and we can collect the different coefficient, different exponent values. So these are all the components that are available with the mathematical modeling. After that, there is any general procedure available for modeling or mathematical modeling have its own methodology? Yes, which has everything you perform in engineering means you should need the problem. So first you define the problem. After that we can move to problem simplifications and what are all the associated factors available with that problem we can assume. Based on the assumptions, we can simplify the problem. After that, we can try to give the solution for that problem with the time factor, space factor, and subsystems. Any subsystem affect the thing. We can give the solution through them also. If I consider time means rate of change of momentum or rate of change of object from one place to another place, likewise I can give the solution with respect to the problem considered as a force. After that, what is the next step? Yes, data requirement for solution. So all the things we can't perform with the mechanistic model, we can develop the empirical model. If I want to develop the empirical model means I need the data. So data also required for solution. It may be a numerical data, it may be a textual data, whatever may be, we can collect the data for providing the solution for the particular problem. Okay, so next, data requirement for solution, move to data availability. So the math engineer starts to make a solution means he should collect data from the available resources. So he should ensure the data availability. So next, the engineer can move to the problem definition. Again, after collecting the data, again he examines the problem definition. After that, he performs the same step: problem simplification assumption, problem solution in time, space, and subsystems, and data requirement for solution. After this cycle completed, he may decide, so data are available, so that I can frame the model as a conceptual this level. So that next step is conceptual model. After framing the conceptual model, engineer can move to the mathematical model finalizing stage. Here he may perform the governing equations, boundary and initial with the boundary and initial conditions. So if he frame the mathematical model means he should aware about governing equations, boundary and initial conditions. Let's see what is meant by governing equations in our next class. Okay, after that, after framing the mathematical model, he should aware about how can he give the solution for that problem. So there are different different techniques are available, which are analytical, numerical, physical. So which method is suitable for giving solution to that problem, he may decide the solution methodology. After solution methodology, he may develop the model. After framing the model, he based on his decision, he may develop the model. After model development, model validation. After model development, he may perform the experiments again. He may give the real data to the developed model and compare that mathematical model output with the real time output. He compares and validate how much of error occurred with that developed mathematical model. Likewise, he may ensure the developed model's accuracy with the model validation. After that, he may move to sensitivity analysis. Sensitivity analysis, generally the accuracy of the developed mathematical model should be 100. The curve fitting is 100. It may deviate means the plus or minus 10% may be acceptable. So the real time accuracy of the mathematical model is analyzed with the sensitivity analysis technique. After that, model prediction. So validation, through validation and sensitivity analysis, model prediction is evaluated. So after model prediction, the results interpretation is to be carried out with the real experiments. After that, summary and conclusion. We can make the summary and conclusion of the developed mathematical model. After that, we can move to model reporting. Finally, we can report the model. Developed model is this. Okay. For example, if I consider the force means force is a dependent variable which can be affected by independent variables. Those are mass and the acceleration of the free body falling from top surface to bottom surface, which is the force model. So I can report likewise to the society. So these are all the modeling procedure and the methodology available with